you can ask your questions or interrupt me while I'm coding, so we can solve some problems and trying to clear some doubts about the lectures. This entire session will be recorded, so if you miss the details of codes, the session recording will be uploaded to the Canvas, so you can watch them later as well. But better to stay here so you can ask your question and get interactively solve some problems together with me. Yeah, so we can start the session, I guess. We can start the session by some problem that Amir has assigned to you. So I can share my screen first. As you might remember from the second lecture, there was a question to find the number of inversions. So what do you mean by inversions? So basically, we will be given n items, and these items, first of all, maybe I can ask, can you see my screen? Is everything fine? Yeah, great. So we will be given n items. Here, for simplicity, we will be considering them n integers, let's say. So there will be some ordering between them, so we can compare them easily. And let's say A1, A2, ... AN. And from us, ask it to find the number of inversion. What do you mean by number of inversion? We call inversion if there is a following inequality, where count the number of pair of I and j such that I is smaller than j, and the value of I, value of A in the ith position is bigger than value of the A in the jth position. So if we give example, let's say we have 5 numbers, 1, 2, 4, 2. So here, you might count there is 4, for example, for I, if we consider this zero-based array, for I of 0, we will be having 4 j's, all of them are smaller than 5. And for the I equal to 1, we will be having 2 inversions. For I equal to 2, we will be having none of them. So for I equal to 3, we will be have 1. And finally, for I equal to 4, we don't have any j's remained on the back. So in the total, we will be having 7 inversions in the entire array. If you understood the problem properly, we can start coding the problem, the easiest version of this problem. So basically, you don't need to think of some complex idea at the beginning to solve this problem in a, let's say, not faster way.
Tutorial.
Okay, so there is some why is not.
Oh, it's online.
Oh, okay. So we'll be using C++ for the implementation. So let's take it in the comment. So by the way, this is the problem. Maybe I can write here. Problem, count the number of inversions. Okay. At the beginning, I will be, for warm-up, coding the brute force solution for this one. And maybe I can ask a question while I'm coding. So what do you think the time complexity of this brute force, the most naive solution for this problem? We'll be getting some array. And let's assume that array size n is smaller than n power 5. Maybe I can look in the chat if there's answer. So brute force solution would be trying each of the pairs of numbers, I and j, and just count the pairs that holds this inequality. So let's say brute force, and we will be counting the number of inversions in the given array of size n. So I should be bigger than j. Sorry, j should be bigger than I. So here, number of inversions would be this is C++ trick. So you just need to, you can just write following Boolean function and just add up them. What do you think? What would be the time complexity of this algorithm, brute force algorithm? So there is a two loops, nested loops, that one traverses from 0 to n. A second one also, in worst case, traverses from 0 to n. And in total, this would make n order of n square, which is also called quadratic time. So yeah, this is the easiest solution that we can think of for now. What we can definitely improve this algorithm by following much smarter ideas. As you might also see in the lecture, we can use of the different ideas, different divide and conquer ideas for solving this problem faster. And one of them can be using the merge sort. And the idea of using merge sort would be revealed now when I start talk about the solution. But we can at least now see that upper bound for this problem is an order of n square. So our developing solution should be definitely better than this complexity. Otherwise, there is no reason to find out new ideas. So when you write solution, maybe if you don't have any idea of solving the problem, you can start coding the brute force, like trying out all possible combinations to solve the problem, and just find out your upper bound. Like if your solution is, your developing solution is bigger than this brute force complexity, you should definitely look into the more effective solutions. Okay, so here, what we can do as a solution. The thing, we will be using divide and conquer approach. And as you might see from the previous solutions for the maximum subarray sum problem, maybe you remember from the first lecture, we would be dividing. So for example, we have an array and we divide solve the problem recursively by dividing into the two halves in each iteration. So at the beginning, if we have elements from A1 to A2 we divide array into two parts. And let's say we have a problem called with this array. And we just call the same function recursively until the middle of this array. A divided by n. So A of n divided by 2. And afterwards, call the same function for the other half of. So we just call this one, for example, left part and right part. And here, so let's say n divided by plus 2n. And the goal is to solve the problem for each of these smaller version of the problem, and in the end, conquer the answer. The thing here, after solving the problem for the left part and solving the right part, now we need to, for example, in our case, we need to count the number of inversion. In that case, so by the way, here, mid equivalent to the middle of them. So if we have a left point and right point in the array, middle would be just the sum divided by 2. So here, when we have an array that is called entire array, we just divide into two parts. After solving them, we need to count the inversions, for example, in our problem, that holds this criteria. If the I and j, like what you can see the inequality that we are searching for. So we're searching for pairs of ij that holds this condition. And if I and j both are in the left part, so if we divide into the array two parts, if I and j both are in the first half of the array, in that case, this will be counted in this function call, let's say left function call. Because both of the endpoints are including inside of this array, so if we call this function, we can be sure that I and j's that included, that is lies inside this area, this part will be solved or counted. Same for the other part. If I and j that lies in the second half of the array, this will be counted on the right part of the solution. And accordingly, we can think of the only case where the I lies on the left part and j lies on the right part that is not counted after calling two function calls. And for solving that problem, we need to think of much smarter way. Otherwise, if we just iterate over all possible i's in the left and all possible j's in the right, for example, let's say we have a function call of some points L and R is the left and right index of the array that we want from us asked to solve. And for this one, let's write pseudocode in range of, let's say, L to middle point. Middle is basically the sum of this L and R divided by 2. And for that, like for J in mid plus 1 to R, if we just count the number of inversion, like AI is bigger than AJ, this would be exhaustive work. And in the worst case, let's say we just call the solve function for the 1 and n. The first iteration would take n divided by 2 operation, while second loop will also take n divided by 2 operation. And this will again end up with a, like, even though it's n squared divided by 4, this would end up, we just get rid of constants, hence just have a quadratic time complexity. So after calling the left solve and right solve, as we do, so here we should do solve for left part first, solve for right part. So currently we are writing pseudocode. It's not related to any high-level programming languages. So let's say left part, right part. Now, just counting the pairs that I lies on the left part, J lies on the right part, will not be effective with following idea. So we need much smarter idea. What do you mean by smarter idea? So first of all, we can see that these two parts are disjoint. So there is no element that lies in the both parts. So we can think of the problem in different way. If there was some element that's shared by both of them, we might need to be having extra conditions. But here we are free to do anything. Hence, losing the ordering of the, let's say, left part for the array from L to mid, and array from, so we have a right part and left part. Okay, and losing the ordering of the left part will not affect our solution, or losing the ordering of the right part, because we don't care whether this will be, for example, element in this part will be index of them affects to the right index. So they are both completely disjoint. So what I can do by doing this, basically, if I can somehow have the sorted version of the left part, sorted left part, and afterward have the sorted version of the right part, my problem can be much easier, because we might do some tricks to count this part in much effective way. Instead of having n squared operation, we can develop much faster algorithm. What I mean by faster algorithm, basically, when you have two arrays, let's say this one as a, now this is sorted left part, so I will just call it array B. And also we'll have an array right part, sorted right part, we'll call it array C. Or I can call it, let's say X and Y. In X and Y, my goal to count the number of elements from X, let's say, yes, one more time. X in B, Y, I'm trying to count the number of X and Y such that X, number of X and Y, such that X in B and Y in C and X bigger than Y. So basically, I want the following conditions to be held for given two disjoint arrays. So now I will be given B and C arrays. The problem now turns much easier. So for solving this problem, maybe I can listen you if you have any ideas that can share you can share off. We can discuss them. So maybe I can wait 1 minute if you have any solutions. So for example, let's say given two arrays B and C with size of, let's say, N and M respectively. So you can suggest algorithm or solution that is much faster than NM, let's say, where NM is the most naive solution that we can think of, like brute force solution. You just try out all pairs in both of arrays. So this is our current problem to be solved. Let's see the chat if there is any ideas for this problem. So for example, if I assume given arrays are sorted, does it make your job easier? For example, B and C are given in sorted order. If we assume that B and C are given in sorted order, what we can do? If we find, so for example, we haven't seen the binary search idea, so we will not go with that one. But the thing is that whenever our array, let's say B1, B2, Bn, and C1, C2, Cm, we see that whenever Bi is bigger than Cj, in that case, all j's, let's say j primes, in, let's say all j's in 1 to j minus 1 are also in this condition. So it means that whenever you find some j, that Cj is smaller than Bi, all elements in that prefix also smaller than Bi. That's for sure. So whenever you find the maximum j with Bi smaller than smaller than Bi, that means all j's in that prefix, or all j primes in that prefix, is also all prefix elements also smaller than Bi. So we don't need to count them, each of them one by one. So that means we can just add to the number of to the answer just j. Answer, add j to the answer. So if we come to the conclusion, it means that whenever you find, for each given I, you find the maximum j such that it's smaller than bi, in that case, you can add j to the answer. That are the number of smaller items in C array than bi. Okay, and the good thing about the being sorted of B, like array B is sorted, so we can see the monotonicity in the finding J's. So whenever I find the maximum J, whenever I find the maximum J for the ith position, let's say G1, in that case, if I jump to the ith BI plus 1th position, I just go to the next element. That means we know that given array is sorted. Hence, the J that here would be like GI, let's say, would be also smaller or equal than JI plus 1. So that means any element that is smaller than BI is also smaller than BI plus 1. So we can say found the maximum J is also smaller than found maximum J for the I plus 1th position. So we don't need to count again, starting from the first position to come until the Jth position. We can directly start from Ji to find out the maximum J that will be smaller than Bi plus 1. Now it will make sense if we see the code, because otherwise currently it remains as a high-level idea. So for example, if I want to write the C++ implementation here, for each element of the B, you would just have some global J, let's say, that would be just increase while it's smaller than Bi. But we need to be careful of not going outside of the array. So we just have this condition. So J is smaller than M. In that case, we just increase the J. And as we said here, add J to the answer. We just have an answer, let's say, we just add J to the answer. This will be doing same job as following brute force solution. Just count all pairs of triplets that BI is smaller than, bigger than CJ. Yeah, both of these implementations does the same job. However, if I analyze the time complexity, this would be a quadratic time. And here we have a loop that just traverses 0 to n. And here we have a while. This while doesn't, it might be seen at the first sake n square. However, it is not, because here we have a pointer that always increases, but not decreases at all. Hence, it will just traverses the C array once. So the complexity of this would be just n plus m. Oh, sorry, here it should be nm. This is drastic improvement, and we can use in our solution for counting the number of inversions. So here B would be what? Like B would be left part of A, and C would be right part of A. The important part here, we assume that B and C are sorted, and that merge sort idea comes here. We need to have B and C that comes already sorted. Otherwise, we might need extra effort to here sort them using some existing sorting algorithms. Faster ones can be, for example, insertion sort, or already C++ implemented sorting algorithm that all works in n log n. So here at the pre-computation, if we don't have a sorted arrays of B and C, in that case, we might need to do extra operation of n log n plus m log n. So this will be extra cost that we need to handle. But if we want a linear solution, in that case, we would be happy if the B and C would come as sorted. to this part of the algorithm, and so we can have the linear time algorithm. Let's go to the implementation side. I would be not losing these files because I can use them in the main algorithm. So I will take all this in the comment. If there's any part that doesn't make sense, you can definitely ask. I can come again and explain that. And yeah, so here we have a brute force algorithm. Maybe I can use of vectors here to see not have any global elements here. So for example, I will just have A here. Definitely we will be passing by reference, otherwise it will just clone the entire data structure, and this will be using extra memory that we don't want. So we'll just have a vector here as well. But let's go A. And I'm using here input output in a C format. So hopefully this makes sense to your side. It's not a hard thing to learn, but we can see that input output of C++ is a little bit heavy. So in online submitting for the problems and solving problems and submitting to the online judges might be effective if you would use the C implementation of having input and output. Yeah, here we just send a vector and can get the size of vector. Vector is a C++ or data structure that you can use for having, let's say, your dynamic array. So this is some type of container that you can have a size, reach some position, all in just constant time. Yeah, so we just missed one letter here. So we have brute force. We can just have the brute force as well here. So we can compare the answers to make sure our algorithm is correct. So let's have a function that calls inversion. And this will take array with the reference, of course. And as we know, in the divide and conquer approach, we need to have a base case. So base case is whenever, so let's say n is the size of array. Actually, we need also ln r that are the left and right pointers of our current solving problem. So here we just need to have a call the function for entire array and from 0 to n minus 1 position. So we are having zero-based container for the saving elements into the vector. So here we just need to check whether ln equal to r. So we will have a single element and number of inversions for the single element is just 0. Cool. Here we want to have the middle of the left and right. Oops. And at the beginning, we just want to call the left and right part to solve them separately in divide and conquer approach. So we just call the same A with L and midpoint. And we just call the same recursive function call for the right point. Now the main part comes. We just assume that we count the number of inversion in the left part, count the number of inversion in the right part separately. Now it's time to count the number of inversions with I is in the left part, J is in the right part. And we want here that both left and right part are already sorted inside. So that are the requirements for solving problem here. And we'd like to use the following algorithm that we have implemented here. So basically, let's say, okay, so here we will have returned some number of inversions in the left part. So let's have some answer here to add them. So we'll add number of inversions returned from the left part number of inversions returned from right part. Now we need to count the number of inversions in current part of the array. So we need to add answer. As we said, I should be in that part. So here we need to create our B and C arrays. As we said, B is the left part, C is the right part, yeah? And both of them are sorted. So we just need to have two vectors here, let's say B and C. And B would be the left part. So start I from, let's do it like this, to the midpoint, B pushback. Pushback is the appending element to the end of the vector. So we just add AI, and we do the same and start from mid +1 to the R part. So now we have a B and C. The B is the left part. Sorted left part of A. Sorted right part of A. Okay. And afterward, we just need to pass this algorithm that we implemented here, that we want to count the number of, what was the problem that we reduced? This one. Given arrays, given two sorted arrays, B and C, of size n and m, count the number of x and y such that x is in B. So B is here, left part. So we just want to actually mimic this algorithm, like number of inversions that I is in the left part, J is in the right part. Because if both of them in the left part, we already counted in the recursive call. If both of them in the right part, we already counted. So we want the special format, like here, left part should be now B, and the right part would be C. So we just want to count the reduced problem into this manner. And we solved this problem before starting our original problem. Like we just have both of them sorted. So we just have a pointer that finds the maximum J such is smaller than BI. So we need to define here N and M. N would be just size of B, and M would be just size of C. Yeah, and we can return the answer in the end. So that's great. If we analyze the time of complexity of this, we would see that we have a T of N that calls two recursive calls that, for example, divide into two parts and just calls the same inversion function, plus O of N plus M, where N is the left part, M is the right part. Both of them has a N divided by 2 here. I believe you might be remembering this part from the same Mercer or other recursive divide and conquer problems that we have solved already. And this will just end up with the O of M log N. But we forgot one part here. Can any of you detect that? Like what part might be missing in this portion of code? Is there anyone? So we just assume that both of the left and right parts comes a sorted order, in a sorted order. However, we haven't changed anything on array A, so it might be not sorted at all. So here we need to sort the left and right part. Like I could just follow the C++ implementation, and afterward having B and C, I could just say, oh, sort the B and C separately. However, this would be having extra, as I said, N log N, where N is the, sorry, M log M plus N log N, where here it's the N divided by 2 actually. So it will be having extra cost of n divided by 2 log divided by n. This is the extra complexity that would add up when we compute the overall complexity. Like I just wrote the same thing. Oops. So that is the thing. Instead of our desired complexity of having just of n divided by 2. Sorry, of n. So this is just because of sorting them here, like left part and right part independently. Instead, we could use Mercer idea in the same algorithm. So we just use them together to have our desired complexity of having n log n in the end instead of L n log n squared. This one would have an upper bound of n log n squared. Yeah, the log n factor also matters a lot when n gets bigger. So we just want to have the most effective one. And yeah, so here, instead of using sorting algorithms that is C++ embedded functions, we just use the Mercer idea in the same algorithm to have B and C, like left part, and maybe I can just change the names. So instead of saying B and C, I can say left A and right B, right A. So it can make sense to you. Okay. I think we are good. And here, after counting our inversions that we are intended to, we just sort the, so now A, L to M mid is sorted, let's assume. And A mid plus 1, which is equivalent to the left A and right A is sorted. Now we want to sort the entire range from A, L to R. For that, we can follow the Mercer idea. What was the Mercer idea? We just look onto the first position of the left part and first position of the right part, which are the smallest elements in both of the parts. And small of them would be the smallest in entire array. So we just put the which one is smaller and just increase our pointer and just continue the Mercer idea. And we can do following. We can have let's say some pointers for the left part and pointer for the right part. And I will write the while condition later. Here, as you might remember from the second lecture, we just say we can put left parts. So we have a two array, left A and right A. So currently, left P would be showing the current arrow to the, let's say, current element that we need to proceed. So we have a right P. At the beginning, both of them is 0. So both of them showing the smallest elements in those sorts arrays. So we just need to compare them. So we just take them. And if it's smaller than right part smallest element, in that case, we need to put to the leftmost point of the A, which is L, the smallest element. Here, after putting the thing, we just need to increase left to the left pointer to the 1. So it feels like we just removed that smallest element. But we need to be careful that one of these elements might not exist. Like left P might reach to the end of the array. In that case, we put the left pointer showing element whenever this condition holds, or right parts element not exists. So right parts element not exist whenever right P is equivalent to what? M. M is the size of the right part. So otherwise, we just put to the next smallest element of entire left to right array, right A's, right P. And we just don't forget to increase the right pointer. And whenever we put the smallest element, we just increase L here. L was showing the leftmost point. Now it's increasing to the onto right. So we can do the L this while L goes to R. Yeah, this is the merge sort part. Like we just had a sort two arrays, we just merged them. So the total complexity would be just of R minus L, which is of linear in the size of two arrays. Yeah, that's great. We can run the algorithm and see whether we count the number of inversions correctly. What was our test case? We deleted. We can write new. 5, let's say 4, 3, 5, 1, 2. The number of inversions would be 3, 5, 7. Yeah, 7, I guess. 7. This is the input. Let's see. Error. It says N and M problem. So we don't use this N here. Yeah, we just count the number of inversion correctly. And even we print the brute force solution and our solution output, we should see the same answer. Brute force output and our solution output. Let's see both matches or not. Yeah, both of them matches. If we come to the analysis of the time complexity, as I said, we just divide the array into two parts, and we call each of the recursively to the half of the array twice. Later, we just have a separate these arrays into left and right part, and we just count the number of inversions with this linear algorithm. And also we finally merge the two sorts of arrays to have an entire range, current range scope would be sorted for the next iterations in the algorithm, because we just assume here both left and right part comes sorted to apply this linear time algorithm. I believe you could also do instead of taking these two parts into two separate arrays, you could do this counting while you merge two arrays. For example, it could be like this, I guess. So for example, I could do like this, I guess. Whenever I put, so we have a left pointer, leftmost element, the smallest element of left part, smallest element of right part. And when we decided to put the smallest element of left part, we just consider the right part's existing pointer. So if we have already put, let's say, two elements from right part, that means we decide to put the next element of left part, means that these two elements is already smaller than the current element in the left. So we can, when we decide to put the element from left part, we can add answer the number of smaller elements in right part by having right pointers current showing place like right P. So right P means here next smallest element in the right part. And whenever we come to some middle part of the left part and decide to put as a next smallest element, that element means that all elements in a zeroth to the right P minus 1 in this part already smaller than the all elements in right part of right part is smaller than current showing left parts element, which is left A, left position. So all elements in this part in right side is smaller than this element. So we can directly add answer. Can add answer number of small elements, which is like that. Actually, I wrote here right by having right P. So which is right P there. So we just add answer this element. And what I mean, just single line of code, we just say right P. At the beginning, it's 0. And as the right P increases on the right part, we see that all these elements is smaller than the next time when we decide to put elements from left part. I hope this makes sense. Yeah, here, what's M? M is the size of the right part. Actually, we need right P and left part. Okay, we can. And let's see whether we have the same answer. Oh, 0. Should be or like should be either end of the right part not exist or we just compare it. Yeah, answer is 7. So this again in linear time, and we can get rid of this independent part. So we just count the number of smaller elements in the right part for each element of left part, while we just merge these two sorted arrays. Actually, we could also get rid of this extra memory overhead by directly working on the left and right part. So instead of saying we just go from left P 0, we just start from the Lth position on the left and right mid plus 1 position and directly work on the eighth array instead of just copying them into some part and just creating n log n extra memory for each part of the execution. But let it remain exercise to you. I would be sharing this code to you. Maybe I can send it together with this recording into the canvas, so you can have entire this file with the comments, understand it more in the future.